So in this problem, we have a vertical spring in which we attach a mass of 0.6 kilograms. Now I have this spring drawn by itself, unstretched, over here. And in this state, the equilibrium position of the spring lies along this red line right here. Now if we were to attach a 0.6 kilogram mass to the end of the spring would get stretched out to a new equilibrium position that lies along the blue line right here. Now this blue line is what we consider to be the equilibrium position that we use in vertical spring problems. Now let's take a closer look at what the problem means when it says the mass is attached to the spring and then released. So in the first spring we have here, we have the spring all by itself, completely unstretched. Now in the second spring, we've attached the mass, but we're still supporting the mass, preventing it from stretching the spring out. Another way of thinking about this is if we had a hand here supporting the weight of the mass. Now when the problem says the mass is released, it means we're taking away our hand and letting the mass pull the spring downwards. In other words, the mass is allowed to stretch the spring out and cause it to begin oscillating. Now the spring is at its positive amplitude at the beginning of the oscillation when we first release the mass. Now at its positive amplitude, the spring's velocity is 0 meters per second, and its acceleration is directed downwards. Now when the spring reaches its equilibrium position over here, and while it's oscillating, which is the same thing as what I drew on this side over here, its velocity is downwards and at a maximum. So when the spring passes through its equilibrium position, its velocity is at a maximum, and its acceleration is actually equal to 0. And finally, when it gets to its negative amplitude down over here, the velocity of the spring again is 0, just like it was when it was at its positive amplitude, except this time its acceleration is directed upwards. And then over here to this spring to the right, we have over here, we have the spring recoiling back upwards, and as it passes through its equilibrium point, its velocity is again at a maximum, and its acceleration is 0. And then up here, the spring has returned to its positive amplitude and has thereby completed its cycle. So another thing to note is that the magnitude of the spring's acceleration is at a maximum at its positive and negative amplitude. So at its positive amplitude over here, the magnitude of the acceleration is going to be at its largest during the oscillation, and it's directed downwards. And likewise, when it's at its negative amplitude, its acceleration, the magnitude of the acceleration is again, it's going to be at a maximum. However, this time the acceleration is directed upwards. So essentially, the acceleration of this spring is greatest at its two amplitudes. However, the difference between the two amplitudes is that the direction of the acceleration is reversed. Now in part A, the problem is asking us for the extension of the spring when speed is a maximum. So from the discussion we just had, we know that speed is maximum when the spring is at its equilibrium point. So let's take a closer look at the spring in this position. Now the extension of the spring is essentially just going to be the distance between the spring's positive amplitude which is right here, and its position at its equilibrium point, which is right here. So it's basically going to be the distance right here. So we're going to call that change of x, and that's going to be the extension of the spring, or the value that we're trying to find. Now we can calculate this extension by doing a force analysis on the spring and mass at its equilibrium position. So I'm going to redraw the spring at its equilibrium position down here, and we're going to perform a force analysis. So when we say that the spring is at its equilibrium position, that means that there is no net force acting on the spring in the y direction. This is also a reason why the acceleration on the spring as it passes through its equilibrium position is equal to 0, because there's no net force acting on the spring. Any forces in the y direction on the spring at its equilibrium position cancel out and add up to 0. So we know that we have a gravitational force acting on the spring directed downwards. Because the mass is stretching the spring downwards, we also have an elastic component pulling the spring back upwards, and these two forces cancel each other out to make it so that our spring is at equilibrium. Now the magnitude of the gravitational force is simply going to be equal to mass times gravitational field strength, and m is going to be equal to 0.6 kilograms, which is the mass of our block. Now we can calculate the magnitude of the elastic force using Hooke's law, which states that the elastic force is equal to negative of our spring constant, which is k, times the distance that the spring is stretched. Now the distance the spring is stretched, or our change in x, is going to be equal to the extension that we're trying to solve for right here. So if we can solve for this change in x, we can find our answer. So rewriting these equations up here, like we said, we know that the net force in the y direction has to equal to 0. So our net force is equal to 0. So that means that the elastic force plus the gravitational force to also equal to 0, which means that the gravitational force is equal to negative times the elastic force, which makes sense because these two forces are directed in opposite directions. And so for Fg, we can plug in mg is equal to negative times negative k delta x, which is the change in position of our spring. These two negative signs multiplied out cancel one another, so we just end up with mg is equal to k times change in x. And so for our mass, we can plug in 0.6 kilograms. G is 9.81. And then K is given to us by the question stem to be 15 Newton meters. So plugging all these values in, we end up with an extension of 0.39 meters, which is the answer for part A of the problem. Now, as for part B of the problem, where we're asked to calculate the magnitude of this maximum speed, we can use the equation from our formula sheet that states that the maximum velocity of the spring is equal to the angular frequency of the spring times the amplitude. of the spring. So one thing to note is that the extension of the spring that we calculated up here, which was 0.39 meters, that is actually going to be equal to the amplitude of our spring. So recall that amplitude is essentially just the distance between the point where the spring is at its positive amplitude and the point where the spring is at its equilibrium position. So it's essentially just equal to the extension of the spring that we calculated in part A. Now, as for the angular frequency of the spring, we can use another formula from our formula sheet that states that angular frequency of an object in simple harmonic motion, like our vertical spring here, is equal to square root of the spring constant of our spring divided by the mass of our spring. And so our K constant, again, was provided by us by the question, and it's 15 newtons per meter, and the mass is 0.6 kilograms. So plugging these two numbers in, we get the angular frequency to be equal to square root of 25, which is equal to 5 radians per second. So we can just plug that value right here. And plugging those two numbers in, we get the maximum velocity of the spring and its oscillation to be equal to 1.95 meters per second. And if we round that, we get 2 meters per second, which is the answer to part B.